Hello everyone, I'm Ved Shanbhogue. I'm with the Rivos. My co-presenter Perrin Perez, who's with Sci-Fi, could not be here, so I'll be speaking for both of us. So we'll talk about IO virtualization and the IOMMU. I'll keep it very high level. We've got a lot of material to cover, so I'll be skimming upon little things, but I hope to give you a good overview of what we are doing here. To start with, just a quick recap on I/O. Most I/O involves doing some kind of direct memory access, wherein, say, a driver sets up a memory buffer for the device to read or write to, sends it a command. And traditionally, that's been in the form of providing the I/O device with a physical address and asking the device to deposit some data into that memory buffer or read out of that memory buffer and do something with that. More recently, there's been a new model evolving, calling it the shared virtual addressing, that allows an application to program a I/O device with a virtual address as opposed to a physical address. And in such cases, the I/O devices have multiple, say, process contexts, and they can access memory buffers using a virtual address. Now, it has the benefit that you can, share a virtual address between the CPU and the I/O, allowing you to, in the I/O, to work on, more richer data structures like, trees and lists and so on. Right? Now, the thing to call out here is that in the case where you're using physical addresses for I/O, there's always this concern that the device might get misprogrammed by the driver with a bad physical address, and it might, inadvertently trample on data structures in the that it was not supposed to access, or the device might be malicious and try to, corrupt your memory. And when you're using virtual addresses, you need a way to translate that virtual address to a physical address so that the device can access the backing memory. So the key thing I want to call out here is that in order to do these protections and translations, you need a memory management unit, an MMU for I/O, or an IOMMU. So now, typically, an IOMMU sits between the I/O device and the fabric that connects that I/O port to memory, and it gets programmed with a page table to do the address translation and to enforce protections. But unlike a CPU MMU that is always operating on a single context at a time, it gets context switched as applications are context switched. And IOMMU needs to deal with multiple contexts concurrently because multiple I/O devices might be accessing memory in an interleaved manner. And that's where we have this concept of a directory wherein for each device that can access memory, the IOMMU needs to go find a context for that device. And that context is obtained using an identifier which we're calling generically a device ID. If you're familiar with the I/O protocols like PCIe, that device ID would be something like a bus device and function number that identifies the originator of that memory access. So now once you found a device context, in addition to providing certain attributes for doing the address translation, it provides you a pointer to the corresponding page table, and you can use the virtual address that came with the I/O transaction, be it a physical address or a virtual address, to traverse that page table and obtain the physical address and permissions. Now, when you're using the shared virtual addressing model, in addition to providing the device ID, the device also provides you a process ID to identify the process context for that memory access. And now there is an additional level of indirection wherein there might be multiple process contexts that are active in the device. And so using the process ID, you need to obtain the process context, which usually is provided through a data structure like a process directory. And now your device context provides you a process directory pointer, and your process directory indexes into that process directory to find the page table to do the address translation. So now once you have this system in place, the IOMMU can provide you the address translation functions. It can do the permission checks and solve some of the problems that we talked about in the previous slides. Now, all that works fine when you have a non-virtualized system, but what happens when you have to provide devices to virtual machines? Right? So if you recall the H extension, it provides a way to virtualize memory for virtual machines. It does that through the use of a second page table called the G-stage page table. So unlike a physical operating system in the virtual machine thinks it is operating on physical addresses, but it's actually operating on guest physical addresses. And there needs to be a conversion from the guest physical address to a physical address in order to actually access the memory. So in order to do this pass-through of devices to the virtual machines, the IOMMU also needs to employ similar two-stage address translation so that operating systems and applications inside a virtual machine can program the I/O devices with guest physical addresses or virtual addresses that need to be translated to a guest physical address and further to a supervisor physical address. And so that's where IOMMUs employ two-stage address translation, wherein the device context, in addition to providing, for example, pointers to the process directory, would provide a pointer to the G-stage page table, which provides the guest physical address to the supervisor physical address translations. And this page table is typically controlled by the VMM or the hypervisor. And the process contexts, which are typically controlled by the VM, they provide you the VS stage page tables. And with these two page tables in place, the IOMMU can do the two-stage address translation. And with this system in place, now the VM can also enjoy all the I/O models, such as direct device assignment and shared virtual addressing, as a native operating system could do with I/O devices. Now, you might be going, there's a lot of data structures to access as part of I/O transactions, because if you do it, say, naively, a two-stage address translation could involve, say, 20 memory accesses in order to find a translation. And so if you have to do 20 memory accesses for every memory access, that can be pretty bad for performance. So IOMMUs try to address some of these performance overheads by means of caching these address translations. And so they bring in this concept of an address translation cache or an ATC. And so with the address translation cache in place, if you've done the translation once, a subsequent I/O access may, if it hits in the address translation cache, can avoid doing those memory walks and thus reduce the amount of memory bandwidth consumed or the latency involved in performing the I/Os. But now, once you introduce these caches, you need a way to synchronize those caches with updates to the page tables. And in order to do that, the IOMMU driver needs a way to issue commands to the IOMMU to do that synchronization. And so that's typically done through some kind of a command queue, and wherein the IOMMU driver can instruct the IOMMU to invalidate previously cached translations if they exist, and so synchronize itself with updates to the page tables in memory. Once you have page tables, we said you can do address translations, and it's natural that if you, as you're doing address translation or permission checking, you might encounter faults. Right? And there needs to be a way to report these faults back to the system software for it to do something about it. Again, drawing the contrast between a CPU MMU and IOMMU, unlike the CPU MMU, where it can stop and report a fault synchronously, and IOMMU cannot report a fault synchronously because the IOs don't stop. And so typically an IOMMU has a queue where it can queue up faults while it continues handling other IO transactions, while the system software can go deal with the previously a fault that occurred previously. And so what the IOMMU would do is, report to the fault queue the identifiers of the IO transaction, the virtual address that is associated with the IO transaction, and interrupt the IOMMU driver so that it can go deal with that fault. One thing to call out is, unlike CPU faults, typically I/O faults are not recoverable if the device has, for example, done a store to memory, and if that store faults, the IOMMU cannot infinitely buffer the data associated with that store. And so in most systems, I/O faults are not recoverable. But can they be made recoverable? That's where some of the protocol extensions introduced by PCIe come into picture. So I'm going to, this is a very busy slide, so I'll try to run through it by pointing to these numbers. So the key enabler of making these faults recoverable is to move the address translation cache from the IOMMU back into the device itself, so that the device obtains a translation ahead of doing the I/O itself. And so the device, before it makes an I/O, it reads an address translation from the IOMMU. And if there's a fault that was encountered as part of reading the address translation, now the device can queue a page request to the system software asking for that page to be made resident. And when that page request message arrives, the IOMMU can place it in a page request queue, interrupt the IOMMU driver, and say, you asked your I/O device to do I/O, but that page is not resident. Can you please make it resident? And the system software, after dealing with that page request, can send a response back to the device, and then the device can retry the I/O. And this way, a number of these faults, they can be made recoverable. Having device-side address translation caches has other benefits because now the device can size its address translation cache based on its I/O needs, and it is less susceptible to being polluted by I/Os made by other devices and so on. And it also allows the device to prefetch these address translations ahead of time so that it can reduce the latency involved with I/O. So these protocols, the address translation service and the page request interface, enable the use of address translation caches in devices, avoid pinning memory as part of I/O, and especially with shared virtual addressing, allow direct I/O submission by applications. Now, where do we put this IOMMU? There's a variety of integration models possible. One of them, I'll just illustrate a few of them. You could have a dedicated IOMMU integrated with an accelerator on I/O device. So this is the case where you size that IOMMU to precisely serve the needs of that accelerator device. A second common model is to have a shared IOMMU where a device is connected to to an IOMMU either directly or through a root port. And now multiple I/O device transactions, they use that shared IOMMU for address translation. A third possible model is where you have a centralized IOMMU page table walker, but then distributed address translation caches that are closer to the I/O bridge that connects to those I/O devices. Now, in a typical system, you might have one or more of these, depending on the needs of the system. So it isn't necessary that you have to have one of these. You can have a mix of these models. Now, from a typical software model, a very popular model is VFIO, which is the Linux I/O virtualization framework. And the IOMMU driver usually plugs into this VFIO IOMMU layer, which provides an architecture-agnostic interface to perform this I/O management. And the IOMMU provides a memory-mapped register interface for the IOMMU driver to configure the IOMMU. And we talked about these loosely coupled queues in memory through which the IOMMU driver can submit commands to the IOMMU, receive notification about faults, and page requests. So to summarize, the IOMMU technology, it unlocks a slew of new and exciting capabilities, such as being able to pass through devices to virtual machines, support shared virtual addressing, support the address translation and page request interface, provides better security and fault tolerance to the system. And the IOMMU is a critical component to address the functional security and safety requirements across a wide array of usages across segments. So the IOMMU TG is working on defining an IOMMU specification for RISC-V to support these requirements and more. There's a link to their GitHub. Please check them out. Thank you.
All right. Questions for Ved? Oh, you're thinking about it? You got it? Okay, here we go.
Sir, can you move your slides back?
Sure.
Maybe 3 pages. 2, yes, here. So from this page, I see you are running 2 IOMMUs. One on the left, one on the right. So does you meaning they are running separately, 2 IOMMUs?
You mean the one on the far right?
Yes.
So one on the far right, what I wanted to call out was there's 2 address translation caches, so think of them as TLBs, that are located closer to the IO bridges. But if any of those address translation caches have a miss, then they ask a common shared page table walker to go find that address translation for them and provide the translation back to the cache.
Oh, okay.
So this allows you to minimize, distribute the ATCs, but then still have a centralized page table walker.
Oh, okay. Thank you. Thanks.
So it works as one unit, essentially.
That's right.
Yeah, okay. Thanks for the clarification. Great question. Other questions? Oh, come on. There's enough arrows and boxes here. Somebody's got a question. Oh, here we go. See? Are you going to stump Ved with this question?
It's a simple one. So the baseline MMU configuration supports page-based memory types. Is IOMMU specification required to support that as well for caching purposes?
Could you, I lost the early part of it.
So the page-based memory types
That's right.
attribution, is that something that IOMMU spec needs to support so that the device knows what cacheability attribution are?
Yes, so the IOMMU does support the page-based memory types.
It does? Okay.
And in addition to being able to provide the attributes, especially when it is coupled with something like CXL, it's also used to determine whether you should make the access using the current cacheable interface or through the IO protocol. Right.
All right, great question. Another one? See? Hey, we're on a roll here. 3 in a row.
For the ATC, I'm curious, how do you enforce the any synchronization regarding invalidation of entries?
So in the RISC-V IOMMU specification, we're defining commands that are very similar to the SVENS or the sinval commands instructions for the CPMMU. So they allow you to do a variety of invalidation operations on the cache translations, right? So all the way from invalidating all translations for a guest context to a single address invalidation.
All right. Let me check. I don't see any online. I have one last question here, and then we'll get you to break. Oh, now I have a decision to make. I have 2 hands up. I'm closer here.
Hi. Is there an impact on any fabric protocol? For example, DVMs from Chai?
So the IOMMU itself, as you see, is not in the path of I/O. The IOMMU is located as a look-aside entity. So it's usually the I/O bridge that deals with the I/O protocol, the fabric interface, and the IOMMU has an address translation interface defined through which the I/O bridge can invoke the IOMMU to obtain a translation. But otherwise, the IOMMU is mostly agnostic of the I/O fabric protocol
Thank you.
itself.
All right, Ved, I'm going to ask the guy who had his hand up to close with you over break.
Okay.
Let's give Ved one last round of applause and thank him for his presentation.
Thank you.